So just to introduce myself, my name is John Goold, and I'm a PhD student in the ultra-cold quantum gases group here in the physics department in UCC. And tonight I'm going to talk to you about a fundamental physical effect known as quantum entanglement. And as the title suggests, I hope that you'll all find this a little bit shocking, a bit weird, but really useful. So when I first came to put together this talk, I was looking for an apt quote from a famous scientist. But I couldn't really find any. So instead, I turned to Eastern philosophy and to the Council of Buddha. And so you see here, all things appear and disappear because of the concurrence of causes and conditions. And what's crucial is, nothing ever exists entirely alone. Everything is in relation to everything else. And it's a really lovely, deep quote. And I hope by the end of the talk, you'll understand the relationship between this and what's known as entanglement. So, just to outline my talk. So first of all, I'm going to talk to you a little bit about classical correlations, what they are. Next, I'm going to talk to you about quantum correlations, otherwise known as entanglement. And I'll give you a brief historical overview there. Then, I'm going to talk to you a little bit about what this entanglement is good for, okay? What we can do with it. And then push into my own area of research, which is cold atomic systems. And I'm going to talk to you a little bit about a very specific problem I've been working on measuring the entanglement between two cold atoms. Okay, so to begin, classical correlations. Okay, so correlation, the word itself. Now, some of you mightn't be familiar with this word, but certainly you're familiar with the concept. Okay, so take this clip from an old Western movie here. You have Lee Marvin holding a cashier at gunpoint. Okay, now we assume at this point-blank range that Lee Marvin would shoot, but he'd never miss. Okay, so what we can say here is, if we look at the gun, we can see that it's either fired or not fired, okay? But from this information, we can automatically infer the state of the cashier. So if we see the gun to be fired, we'll automatically know that the cashier is dead, and vice versa. We see the cashier to be alive, we'll automatically know that Lee Marvin hasn't fired his gun. And this is what's known as a statistical correlation between two events, okay? Very simple. Now, an example of this, for example, is an example of 100% correlation, okay? As strong as you can get. Now, what's an example of a 50% correlation in this situation would be, let's say, if Lee Marvin, 6-bullet chamber, puts 3 bullets randomly in there, and there's a 50-50 chance of the cashier being dead. So everybody gets the idea. But I'm here to talk to you a little bit about quantum mechanics, okay? So what is quantum mechanics and what does it describe? So as Brittany says here, quantum mechanics really is the set of rules which govern the very small, okay? But unlike her bike here, as Isaac Newton would rightly point out, would obey the laws of classical mechanics like you learn for your junior cert. But quantum mechanics really is the science of the very small. So pick a spot. Smaller than the hair length, okay? It's smaller than the level of biology, the dirt in our hair, okay? It's smaller than the molecules that make up the bacteria, and you really are down to the level of single atoms and the interactions that are between them, okay? And just at this level, things get very strange. Here's an artist's expression of just how strange things are. You really are in an Alice in Wonderland type situation in many respects. Now, one thing that becomes particularly strange are correlations, as we've discussed before. So what happens to these correlations quantum mechanically? Okay? It's a really good question, actually, and it was a question that was asked in 1935 by Albert Einstein and 2 of his colleagues. Okay? And what they found was, in quantum mechanics, the correlations are actually greater than 100%. That's really weird, right? Okay, so what they considered was the following thought experiment. 2 particles that interact in a very specific way and then fly out across the laboratory, or if you want, across the universe. What they found is if you made measurements at a distant point A, then they'd automatically influence the outcomes of measurements at point B. Instantaneous really is the key word here, okay? Faster than the speed of light, which, to Einstein's disgust, he called it spookhaften verworken, spooky action at a distance, and he really thought that it was testament to the fact that quantum mechanics actually is wrong or flawed in some way, okay? This actually is the headline from the New York Times of the day, just to show you, or give you an example of how much of a controversy this actually was, okay? He really believed that all realistic physical theories should be what he called local, that you shouldn't be able to influence the outcomes of events in a remote location. Okay? But to take you up to present day, okay, some of the history behind this. So the guy up here is Erwin Schrödinger. And many people don't know this, but he was actually an Irish citizen, a Nobel laureate, for his contributions to quantum physics. And he said that we should really take this spookiness seriously. He called it verstrashtum, or entanglement. Okay? But the problem with this was, at the time, experiments were rather primitive. There was no way of really testing who was right, Einstein or quantum mechanics. Until, enter John Bell, another Irish connection. He was a Belfast man, a graduate of Queen's University, Belfast. And I think he is probably the most underrated scientist, not just in Ireland, but in the world. And what he did was so important was that he was able to think about an experiment that you could do in order to see who was right. He derived a set of inequalities called the Bell inequalities, which, when violated, would say that quantum mechanics really is this spooky thing, and if they weren't violated, then Einstein was in fact right, and the universe doesn't behave this way, quantum mechanics is wrong. But of course, still, experiments a bit dodgy. It took another 20 years. This guy here, Alan Aspect, for his PhD thesis, actually performed an experiment using what particles of light, so called photons, which are essentially the light analog of the atom, and he was able to do a Bell test the Bell inequalities. And much to the joy of the New Age hippies of the time, they found that the Bell inequalities were in fact violated, and the universe, at least at the quantum mechanical level, was behaving in this very strange way. Okay? But, much to the abhorrence of the conservative scientists of the time, they had some qualms with the experiment. But let me tell you today that with photons at least, Bell's inequalities have been violated over longer and longer distances. They did this in 2005 over the city of Vienna at night. They did it last year over the Canary Islands where you go on holidays. And there's an ongoing project with the European Space Agency to violate Bell's inequalities in outer space. Okay? So one may pose the question, what really is the use of doing this over longer and longer distances? Well, it turns out that some clever people in the early 90s thought, well, you can use this entanglement to really do some useful stuff. Okay? And this is the kind of emergence of this whole area called quantum information technology. So there's three main areas, one being quantum cryptography, okay? So you can imagine that if you have this event that happens, that if you make measurements and you know they change things, then you could use it to encode or encrypt information like very, very securely. And I think they actually use this in a bank in Zurich. The other area is quantum computers. You're going to hear about that later on tonight. And one very, very strange thing is quantum teleportation. They can actually use sharing of entangled pairs to teleport the state of an atom or a photon in the laboratory. It's really not science fiction. In fact, this guy here, Anton Seilinger, has done this in the lab in 1998. And even he's done it over larger distance. You see this schematic from a Nature paper where he has done it over the River Danube. Okay? So it's really, really real science. Okay? So where do I come into this? It just so happens that in recent years, it's been identified that this phenomena, or this strange correlations known as quantum entanglement, actually appears in a wealth of physical systems. And one such physical system is cold atomic systems. So cold atomic systems are systems where the atoms are trapped at really, really cold temperatures. So they can really isolate single atoms in the laboratory and take pictures of them, which is quite incredible. So here's an experimental picture from two microtraps in Dorset. They do this with magnetic fields, and another one from Innsbruck in Austria, where they have 8 ions in a row trapped. And my own PhD work focuses on these similar systems, and what I like to do is I like to be able to identify if there's entanglement there, and if there is, can I measure it, and what can I use it for, okay? So take the example here of the two atoms that are trapped, right? For me, a theorist, this is an experimental picture. It looks something like this, okay? Now, one particular problem that I was looking at last year was that if we trapped two atoms in one of these cups, okay, and we raised a laser in between them, so like a barrier. So you can see here, the barrier is very big, the atoms no longer talk to each other, i.e. they don't interact, and we'd expect no entanglement to be there. And what I like to do is, as we lower the intensity of this laser, I'd like to see how does entanglement or do these correlations arise, and see it as a function essentially of the barrier depth, okay? So this is what I really do in my work, and just often people wonder what I do, especially my mother, and I just put this slide here just to tell her, well, really what I do is I like to model these experimental situations. So I really sit down, I scribble things out on pieces of paper, I use the waste bin quite a lot, but eventually I come up with a model which is experimentally realistic, okay? So we like to talk to experimentalists, and I just want to show you some results from a paper which I published last year. which from the same problem. So what you've got here is you've got interaction between the atoms on the x-axis and a measure for entanglement on the y-axis. So 0 being not entangled and 1 being entangled. Okay? So as we increase the interaction, we can see the entanglement is increased between the atoms. Also, the effect of the colour here is essentially the effect of lowering the barrier. So we see the barrier has the effect of decreasing the correlation between it. So what we've got here is we've got a system in which we can control the amount of entanglement between two pole atoms, and we think that this will be useful for people who want to do quantum information technology. So that's about all I have time to talk to you tonight. So really what we've learned here is that entanglement is a fundamental effect in physics, and it's intrinsically a quantum effect, and also that physicists are beginning to be able to harness it and use it to do amazing things. So I'd like to thank you all for your time.